Okay, so hi everybody. So this is our last video for Calculus 1. How exciting. So all we have left is to do a few examples for 7.1, which is all about areas under the curve. On the last video for part 1, I talked about how we're going to find the area under the curve. If our rectangles were vertical, we were going to do the top function minus the bottom function. And if our rectangles ended up being horizontal, which means that if they're horizontal, that means we have a function of y, most likely, then we will integrate with respect to x, and we will do right minus the left function. So let's do this example where we want to find the area bounded by y equals x squared and x plus 12. So now you're probably wondering, well, how do we do this? So the nice thing is that in, I believe, 4.3, we learned about curve sketching. So curve sketching is going to come in handy in this section because you want to have an idea of what your graphs look like to be able to determine which one's your top function and your bottom function. So our goal here is to find the area bounded by these two regions. So we need to find the area bounded by, let's say, this region here, which I'll graph in green, and this region here, which I'll graph in blue. And so when we graph these regions, we need to be able to find the region that we're looking for and also determine if we're going to do top minus bottom or right minus left. So let's go ahead and graph these two functions. Now for my blue function here, this is simply just a line and something you probably should have learned from before. And so this is a line with a y-intercept at 12. Let's say 12 is here. And for these, what I really want you to graph is what's kind of going on with the function. You could do a very accurate graph or you can do a rough sketch of it, okay? And the reason why you can do a rough sketch is I'll show you just in a second how we'll get a little bit of a more precise graph. So this, we have a line with the y-intercept at 12 and a slope of 1. So this graph here looks somewhat like this. Okay, not super accurate or super nice, but something like this. It's a line. And for our green function over here, well, that is simply just a parabola, our basic parabola. So this function looks like this. Oh, that's not what I meant to do. And so when we graph it, what they want to know is what's the area between these two curves. So they want to know this yellow area right here that's in between. And so how exactly do we find that area? So the first thing that we need to do is we see now that our top function is going to be this one, our blue function, which is equal to y equals x plus 12. And our green function is going to be our bottom function, which is our x squared function. So we know that we're going to have to integrate our top function minus our bottom function, right? So our blue minus our green. And that's also because our rectangles, when we draw them, they're also vertical. But now we have to be able to find our a value and our b value in order to be able to integrate this. Because yeah, I can say let's just do the top function minus the bottom function, which is going to be our top function, the one that lies on top is our x plus 12 minus our green function, which is x squared dx. Now I can definitely just go ahead and write this, but the thing is, yeah, sure, I can integrate this, but I will never find the area because I don't have bounds. So how do we find those bounds? I mentioned earlier in the last section that what we sometimes need to do is we need to be able to find out where these graphs intersect. So what we're going to go ahead and do is we're going to look at our x value at this point, and we're going to look at our x value at this point and find out where they intersect. Now, the most accurate way to do this is to actually set the two functions equal to each other. So what you're going to do is you're going to set x squared equal to your x plus 12. And when you set those equal to, they're going to tell you where those x values are intersecting each other. And so if we solve this, we'll get x squared. I'm gonna move everything over to one side. So I'm gonna move the x and the 12 over to the left-hand side and set this function equal to 0. Now when I go ahead and set this function equal to 0, I'll get x plus 3, x minus 4 equals 0. So I get my two x values that are -3 and 4. So this tells me that this point here where they intersect is actually -3, and this point here is +4. So now we know we're going to be integrating from -3 to 4. From our top function minus our bottom function. So this is going to be our top minus our bottom function. And if we go ahead and integrate this, we'll get -x³ over 3. And now I'm just like rewriting them. We're going to get -x³ over 3 plus our x squared over 2 plus 12x. All I did here was rewrite them in that decreasing order that we like. And we're evaluating from -3 to 4. And if we go ahead and evaluate this, I'm going to skip the step where we evaluate them because we've done a few and I don't really want to waste time on this video on just evaluating them. So when we go ahead and evaluate this, we'll get the answer 343 over 6. And this is our final answer. So this is the area of this yellow curve over here. So what did we do? First, we graphed the function to determine which function is going to lie on top and which one is going to lie on bottom. And after that, we noticed that they intersect at 2 points, and that's how we're going to get our A and our B values. After that, we set them equal to each other to find our A and our B values. And then those are going to be, and then we're going to do our top function minus our bottom function. And then we just integrate like normal and evaluate that integral, okay? We'll do a few more examples just so, you know, we get used to this. Okay, so let's do another example. So for this example, we're going to want to find the area of the region bounded by, and this should say by y equals 4 minus x squared and the x-axis. So here we have our function y equals 4 minus x squared, and then they want us to bound it by the y-axis. So best thing here to do is to draw the function. Always draw the function or somewhat of what it looks like in order to be able to identify what region you're looking at. So the function here, y equals 4 minus x squared, is simply just your downward parabola shifted up at 4. So we should be able to get pretty quick at graphing these already by now. So here we are up at 1, 2, 3, 4, and we are downward. So we have a downward parabola there, and they want us to bound this function here by our x-axis. Now our x-axis is this function here. So if we graph it, I mean, I already have it graphed, but just so that you can see it and we can correlate it with this blue color here is going to be that line here. So what they want from us is they want us to actually find the area that's right here. Now, that's not bad. That seems reasonable. So how do we actually find this? So we know that our green function here is the line y equals 4 minus x squared because we were told so. And the line at the bottom is just our x-axis. Well, another way to write that x-axis is to write the line y equals 0. So the x-axis is the same thing as y equals 0, that line, that horizontal line, y equals 0. So we can easily integrate this. Our top function here is our green function, and our bottom function here is our y equals 0 line. And now in order to integrate it, we need to find what this point here is and what this point here is, so that we can integrate the top minus the bottom between those two bounds. So let's go ahead and find that first. So we're going to do 4 minus x squared. And so since our bottom function is equal to y equals 0, we're going to set this equal to 0. So normally we have that equal to a function, but in this case, our bottom function is just that constant y equals 0. And the same thing would have applied if I said, for example, y equals 3, then this would have been the number 3, okay? Just so you know. And now from here, all we have to do is solve for our x values. We solve for x, we're gonna get x squared is equal to 4. So that means that our x values are going to be plus and minus 2, which makes sense. So that means that here, our value is -2 and +2. So now when we do our integration, we're gonna integrate from -2 to +2. And our top function was 4 minus x squared minus our bottom function, which is just 0 dx, because we're integrating with respect to x. And we're integrating with respect to x because, one, we can see that our function is in terms of x. That's one huge identifier that we will be integrating with respect to x. Our right-hand side has all x's in it. Not only that, we also, if we draw our triangles depend on our functions, and our functions are right there. So we can see that we have that vertical line. And so after this, all we have to do is integrate this, and this is the same thing as the integral from -2 to 2 of 4 minus x squared dx, and it's nice because that 0 just really goes away. We don't have to deal with it. We integrate this and we'll get 4x minus x cubed over 3, evaluated at -2 to 2, which is equal to 32 over 3. And so this gives us the area of our yellow region here. Okay, easy peasy. Takes a little bit of getting used to, but remember, always graph your function, always find your bounds if they're not given to you, and then identify whether you're going to do a vertical or a horizontal. And we'll do a horizontal one before this video ends. But more than likely, you will do vertical for the most part, but you should still know how to do horizontal. So let's go ahead and do another example. Okay, so now I want to do a little bit of a different example so I can show you that our top function doesn't always stay a top function, and our bottom function doesn't always stay a bottom function. So just bear with me, and let's do this example together and walk through it. Okay. So for this one here, what I want you to do is they want us to find the area enclosed by 1, the sine function, 2, our cosine function, and pi over 2. So, and then the y-axis. So how do we do that? So we have a couple of factors here. First off, we have our sine function. I'm going to make that blue. Our cosine function, I'm going to make that red. And then we also have our y. And then we also have our x equal pi over 2 function, which I'll make in green. And then we have the y-axis, which I guess I'll make in purple. But if we the first thing that we want to do is, one, graph our sine function and our cosine function. And by now, hopefully, you know how to graph those. Hopefully. Okay, so so the first thing we should do is we should graph these functions. And so hopefully we are all comfortable with graphing sine and cosine. So let's go ahead and do that. So our sine function starts at 0, and then it goes to 1, and then it does the opposite on this side. Now, the left-hand side doesn't really matter, and I'm going to show you why in just a second. The reason it doesn't really matter right now, although it's good to draw in good practice, is because we're looking for the area bounded by our y-axis, which is this purple line. So our y-axis is the same thing as the line x equals 0, and our pi over 2 function. And so this one will stop right here at pi over 2. And so pi over 2 is right over here. And so we're bounded by that. Now our job is to also graph our cosine function, which we'll do in red. And that starts at 1 and then goes off this way. So what they really want is they want the area enclosed by our sine, cosine, pi over 2, and our y-axis. So if we look at where all three of those are happening, we don't really need that piece. What we really do need is what's going on over here. So we're going to find out where they cross each other and where they're bounded by each other. And that's going to happen here and here. Now I want you to notice something, that when we first start from the left-hand side, our red function is above our blue function. And our green, and then as we hit this spot, I don't know what this spot is yet, but hopefully you do. Once we hit that spot, they cross paths, and our blue function becomes our top function, and our red cosine function becomes our bottom function. So they switch places, and we need to account for that. That's very important. So first things first is we do have some bounds here, which we may or may not use, right? I'm assuming we will, but we also notice that they intersect at some point. And so let's figure out where they intersect. You probably already know this answer, but let's just go over the process again so we don't forget. To find out where graphs intersect, we're gonna set them equal to each other. Now this graph is the sine graph and the cosine graph. So that means I need to set sine x and cosine x equal together. Now keep in mind, we're only looking at the time when x equals 0 and x equals pi over 2. So we're looking at a very small interval. Actually, we're looking at that first coordinate of our unit circle. And so if we ask ourselves, where in that first corner of that unit circle, right, on that first quadrant of that unit circle, does sine equal cosine? The only place where that happens is when x is equal to, hopefully you're thinking it, pi over 4, sorry. I kept thinking about pi over 2 over here. It's pi over 4. So that tells us that this spot here, it has to be pi over 4. Okay, so now we have a function from 0 to pi over 4 and pi over 4 to pi over 2. But we also have to account for the fact that when we first start, our red function is on top, and then halfway through, our blue function is on top. So we know that the total area is kind of broken up between two different areas. Let's call this our area 1 and our area 2. And the total area between those is going to be the sum of those areas. But they happen differently. So what I want to do is I'm going to have my total area equal to A, and let's just see how we can write this area 1. So our area 1, we start at 0, and then we're going to stop at the value pi over 4. So that tells me my bounds are from 0 to pi over 4. And now when I'm looking at this function here, I see that my cosine function is my top function, and my sine function is my bottom function is that blue function, which is sine. So if I'm doing top minus bottom, I'm going to get our cosine x minus sine x dx. But again, we're not done. The area is going to be our area 1 plus our area 2. So now if I look at this second area, my integral here is going to be from pi over 4 to pi over 2. But now the roles of my top and my bottom function switch. So that means now my top function is sine x minus my bottom function cosine x dx. Beautiful. So notice that with this one, it was a little bit more complicated because halfway through, we had a switch where our functions then reversed the roles of top versus bottom. And we had other bounds to account for. So just be very careful when you're doing the homework. If you ever notice that the top function becomes a bottom function or vice versa, that means that you need to do multiple integrations so that you actually get the entire area. And then after this is just a matter of integrating each one separately. We integrate that first one. We're going to get the integral of cosine is sine x. The integral of sine x is negative cosine x. So that's going to be plus cosine x, and sine x is negative. From 0 to pi over 4. And then this is going to be plus the integral of sine x is negative cosine x. The integral of cosine x is sine x from pi over 2 to pi over 4. Okay, and now all we have to do is evaluate this. And if we evaluate this, do f of b minus f of a. I'll give you the final answer here, but it's going to be 2 root 2 minus 1 just to save some time. Okay, and then we're going to do one more example. I'm going to do the horizontal case in the next example. Last example here so that I can show you how we'll integrate when we have the horizontal little rectangles. And so in this example, we're going to have the area enclosed by the region x equals 1/2 y squared minus 3. And then we're going to have our line that's equal to y equals x minus 1. Okay, first things first, let's graph these functions so we can see what's happening. So if I graph my first function, x equals 1/2 y squared minus 3, well, that's simply my parabola flipped over on its side this way. And it's shifted over at -3, so at 1, 2, 3, I'm doing something like this. And like I said, may or may not be very accurate, but what I want to do is get a rough sketch. And then after that, I can maybe find the bounds after. But I just know it's my sideways parabola, and I'm getting shifted down at 3. If you want to be more precise, you can plug in a couple more values. But the idea is so that you are able to see top versus bottom function, correct? And so now we can graph the line x minus 1, which is just your regular line shifted down at 1 with the slope of 1. So this function looks like this. Okay, and now so the area that we're looking for is this shaded area here in yellow. And we have two options in order to evaluate this. We can still choose to do what's it called, vertical rectangles so that we integrate with respect to x. We can still do that, but the process becomes a little bit more tricky. And that's because if you notice, one, we're gonna have something weird here if we do that. And second, if I decide to do that, my function is in terms of y. And so if I do decide to evaluate with respect to x, then I have to make this function so that my independent variable is x. Because right here, my independent variable is y, and x is depending on that y value. So the first thing that we have to do is, since we're choosing, in this case, to evaluate that rectangle for the horizontal values, for the horizontal rectangles, we need to find out where they bound each other. And so that means that we're gonna need to set these two equal to each other. But before we set these two equal to each other is here, we wrote this so that our independent variable was y, but here our independent variable is x. And so we have our function x equals 1/2 y squared minus 3, and our function y equals x minus 1. And I know that I'm going to want to set both of them equal to each other. But if I set both of them equal to each other right now, I can't. The reason I was able to do it before was because if I set sine x and cosine x both equal to each other, well, they're both equal to y, so I'm allowed to do that. They're both with the same variable. I can set them equal to each other. In this case, this function here is equal to x, and this function here is equal to y. I can't set them equal to each other as is. But if I change one of them, I definitely can. Easiest one to change is this one. So if I rewrite this so I have my x equals, I will get the function x equals y plus 1. And so we're going to now set these two new functions equal to each other to find the bounds that are here and the bounds that are here. Okay, so then we're going to get 1/2 y squared minus 3 is equal to y plus 1. And our job now is to find out where they intersect each other. And so what I'm going to do is, because I have a fraction, I'm going to want to get rid of it. So I'm going to rewrite this as y squared. So I'm multiplying everything by 2 in order to get rid of that fraction. So I'm going to get y squared minus 6 is equal to 2y plus 2. I'm going to set everything over to one side, set it equal to 0, and I'm going to get y squared minus 2y minus 8 is equal to 0. Now I'm going to factor to get y minus 4, y plus 2 equals 0. And so that means that the y values where they intersect are going to be at -2 and 4. So that means that this spot here, let me go back to red. And this spot here is going to be 4 and then -2. And so now we're going to integrate with respect to y from those two places. So now, since we have horizontal lines, we need to do the right function. Remember that we're going to do our right minus our left. And since we're integrating with respect to y, it's going to be dy. And it's going to be from -2 to 4. Our right function is that green function, which is going to be, so our rightmost function here is that blue line here that's more to the right, which is our line, it was our line x minus 1, but since we want to integrate with respect to y, we want to keep those variables with in terms of y, so we're going to go ahead and use this version of it. Going to be y plus 1 minus our left-hand function, which that one was nice the way it was, which was y squared, 1/2 y squared minus 3 dx. And now we're going to integrate between -2 to 4. Okay. And then from here, you're just going to integrate like normal. This is going to be the integral from -2 to 4 of -1/2 y squared. I'm just simplifying everything. Plus y plus 4 dy. And if we integrate this, we will get -1 over 6y cubed plus 1/2 y squared plus 4y and 4 to -2. And if we evaluate this, I did it ahead of time, we'll get 18. So the trick here is, one of the biggest factors that'll tell you you need to use a y version is if you have a function that really depends on that y value. And if they give you a function that doesn't depend on that y value and you can rewrite it where it does, then go ahead and do so to make your life a little bit easier. Because although we could have used this vertical function, that means that, yes, this one was ready to go, ready to rock and roll to integrate in terms of x. This one wasn't. And in fact, if we were to try to make this one and solve it so that we had our x's, our y equals some x value, at some point we would have to take the square root of each side. And I don't want to integrate anything that has a square root. I'd rather much integrate something that has just powers than a square root. Okay, so that's it for 7.1, and that's it for the rest of the semester.